Okay, now let's look at what if we have our forces. Okay. Now, what if now we have Vz? Okay. So the axis of interest again. Okay. Then where our major web? I'm going to draw that this is our major web now. Right? And then the shear flow. And then here comes our terminal. So we have terminal 1, terminal 2, terminal 3, terminal 4. Okay. And then at the center, you can draw it going in or coming out. Like what I told you, this is your terminal 5. We know that this entire section over here, right? This entire section over here, the shear stress is equal to 0. Because of what? Because Q is equal to 0. Are we clear? Okay. Now let's put in some values in. As I said, I want you to be comfortable. I want you to let's put in some values now. Okay. Let's do a different one. Let's do a different one. So by putting in values, you'll be more like comfortable. Okay. Okay. So over here is our beam. Okay, cross section of our beam. Okay. So we are given that Vy is equal to 2 times 10 to the power 3 pounds. Okay. So given the transformation, this is Y, this is Z, and we are given that the thickness is equal to 0.125 inches. Okay, so the thickness is 0.125. Okay, so we are going to find, okay, the shear stress at point A, B, C, D, and E. Okay, A, B, C, D, and E. Okay, so now we find our major web, I like in yellow. Okay, that's our major web, and then we design our shear flow. This is our terminal. This is our terminal. So we have terminal 1, we have terminal 2. Okay. So formula we're going to use is shear stress. Okay. So the shear stress, the intersecting plane is always the X. Okay. So later we do that. We know that we're going to find the shear stress is equal to what? It's equal to Vy over Izz Qz over T. Okay, that's our general formula. Okay, so now we are going to deal with we are going to find our Izz. first. Okay. So we are so IZZ, right? So the ZZ axis is over here. And by observation, we know that this is the centroid. Okay. So the width is equal to 2.5. The depth is also 2.5 cube divided by what? By 12. Okay. Now we are going to do the two hollow part. Okay. So it's 2.5 minus by 0.125 once, 0.125 twice, 0.125 three times. Okay. Oh, no, hold on. This is plus or minus. Okay. Then that's the width. The depth is 2.5 minus by 0.125. Let me shift. Yeah. Minus 0.125 cube divided by 12. Okay. So this will be equal to 2.5 power 4 divided by 12 is 3.2552. Let me do it. 2.5 times by 2.5 power 3 divided by 12. 3. Minus, so 2.5 minus 0.125 times 3, 2.125. Multiply by 2.5 minus 5.125 minus 0.125 is equal to 2.25 cube. Okay, 2.25. I will not rush, okay, or not. Divided by 12. So this will be equal to 3.2552 minus by 2.125 times by 2.25 power 3 divided by 2.125 times by 2.25 power 3 divided by 12. 2.0171. So the 3.2552 minus 2.0171 is equal to 1.2381 inches to power 4. Okay. Okay. So once we have this, okay. Now to do this, you have to also identify okay, box beam or white flange. Okay. So we know at point E, okay, it is a white flange because you have one terminal and one arrow. Right? At point E, you have one terminal and one arrow. If you look at white flange up to this section over here, right? You have one terminal, one arrow. Very clear. For box beam, you have one terminal, you have what? Two arrows. Can see it. One terminal, you got two arrows, the other one terminal, one arrow. Okay. And the arrow is pointing towards one direction. Okay. So with this, you know that point E is white flange, and its white flange you put down as Q, right? So we know that the shear stress, okay, the intersecting plane is X, yes or no? Because this plane, right, the cross section will intersect the x-axis, okay? So the intersecting plane is X. The shear force is in the Y direction. So at point E, so this is equal to Vy over Izz Qz at point E divided by thickness, right? So QZ at point E, so if we look at the diagram, right, it's at the terminal. So QZ at point E, the width is 0.125. The depth is 0. The Y bar is 0. So this is equal to what? 0. So therefore, the shear XY at point E is equal to 0 PSI. Are we clear? Okay. So that is our point E. Next, we want to find our point D. Okay, so I'm going to copy this, I hope. Okay, it works. Ah! Okay, let me try. Microsoft. Okay. So next, we look at point E. Sorry, D. Okay, look at point D. At point D, right, you have one terminal. You see how the arrow is moving, right? So we are going to focus in this view now. We're going to focus here, right? So one terminal, right? Arrow only one direction. So when that's the case, you can say that point D is also box white flange. And we only need to use Q. Okay. So next we're going to find QZ at point D. Right. So the width is 0.125. The depth is 1.25 minus by 0.125. The Y bar is 1.25 minus by 0.125 multiplied by half. So this will be equal to 1.25 minus by 0.125 squared times by 0.5 times by 0.125. I get 79.102 times 10 to the power minus 3 inches cubed. Let me do it again. 1.25 minus 0.125 squared times by 0.5 times by 0.125. 79.102. Okay, 79.102. So when that's the case, the shear stress, okay, the cross section intersect the x-axis. The shear flow is flowing the y direction. So this is y. Okay. So this will be equal to our V is equal to 2000. Q I is equal to what? I can't remember what's our I. 1.2381. One down here because of Q. Thickness is equal to 0.125. Okay. So 2000 multiplied by 9.102 power minus 3 divided by 1.2381 divided by 1 divided by 0.125 is equal to 1.022 times 10 to the power 3 PSI. Okay. Now let's look at point C now. At point C, the arrow, this is a junction now. Different color. Okay. Now this is a junction, not terminal. And then the junction, it splits into what? It splits into two. Okay. So now if you look at a white flange,